Hello, Year 13. We're starting a new topic today, and it's all about lattice enthalpy and Born-Haber. This topic is going to be completely contained within this one video, so you'll just need to make notes on this and make sure you're refreshing your mind about them before each lesson. A lot of the things we're going to be doing and a lot of the tricky bits of this are about their applications. I will warn you, I'm trying out a new style of making videos today. I'm going to be trying to write along. As you well know, my handwriting is fantastic, so this shouldn't be much of a problem. So here are our specification points. Not too many, and a lot of it is about applications, so we need to be learning some definitions and we need to be learning how to do some skills. So what is a lattice enthalpy? We know a lattice is how ions are arranged in a solid. So the lattice enthalpy is the enthalpy change when 1 mole of ionic solid is formed from infinitely separated gaseous ions under standard conditions of 298 Kelvin and 101 kilopascals. 1 mole of ionic solid, fair enough, formed from infinitely separated. That's not really needed, but it's important. I think it's quite important to know. And what that means is that they were so far apart they weren't exerting any sort of attractive force on each other. Gaseous ions. Gaseous ions is the important bit. Okay, this is different to formation enthalpy. Formation enthalpy is when we form 1 mole of ionic. Well, we form in this state. The formation enthalpy of an ionic solid is when 1 mole of ionic solid is formed from its elements, constituent elements, under standard conditions, whereas we are looking for the enthalpy change when we form from gaseous ions. And what this essentially is a measure of how strong that ionic bond is. Okay, so how are we going to measure that? How could you measure that? You can't get gaseous ions and then suddenly push them together from infinite separation. Well, there's two things I spoke about then. This, going from gaseous ions like this to ionic solid, is the lattice enthalpy. We'll call that LE. This, sodium plus half a chlorine in their standard constituent elements in standard states to form 1 mole, that is a formation enthalpy. So to get from here to here and then round to here, if we found that out, we could make a sort of Hess cycle for it. Thankfully, that is possible. And what we need to know is the energy required, firstly, to go from being this solid and this gas to being a gaseous sodium and a gaseous chlorine in single atoms. Now this is two different things. We've got what's called the atomization energy of sodium and the dissociation enthalpy of chlorine. Let's speak through each of those. Atomization is when you take a solid and you split it up into individual atoms. I'm going to be giving you a definition of that later. And dissociation is when you dissociate a molecule of diatomic gas. Again, definition for that later. It's more important, to be honest, that you know what that means. So the dissociation bit of this is going from half a Cl2 gas to just Cl on its own gas, and the atomization bit is going from sodium solid to sodium gas. Okay, so then we have to go from these two gaseous atoms to two gaseous ions. To go from sodium gaseous atoms to sodium gaseous ions, that is quite clearly the ionization energy. Call that IE. We know all about that. The energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions, unipositive. Now the negative version of that is called the electron affinity, which is the energy required to the energy released when 1 mole of electrons is added to 1 mole of atoms to form 1 mole of negative ions. Okay, now this is kind of confusing and it's not the most. This isn't the standard way of looking at this. This is called a Born-Haber cycle. It's much bigger than a Hess cycle. So what we do is we look at it. This is the standard way of seeing it as a sort of graph. Okay, so you can imagine this graph. We've had a question. There's a question at the top we'll go through in a second. But this is what the graph looks like. You have, at the bottom, you have your ionic solid, in this case, sodium chloride. Okay, so that will always be at the bottom. At the top, well, just above the bottom, we'll have our formation enthalpy. So these are our constituent elements in their standard states. And that is because to go from here down to here is the only arrow going in a different direction. We then have a load of endothermic processes that go up. Atomization, to go from sodium solid to sodium gas. Dissociation, to go from ionization, to go from sodium gas to sodium positive gas. Then we have dissociation, to go from chlorine gas to chlorine atoms. Now notice you had to times that by half because we had half a mole here. We've kept the same quantities all the way up. That's important. Then we've got sodium positive at the top, chlorine not positive, nor is it negative. We need it to be negative, so we have an exothermic process here, the electron affinity, to take us down to sodium positive gas and chlorine positive gas, negative gas, which is then means we've got to the stage where we can draw on the lattice enthalpy because we have ions, gaseous, and we'll assume infinite separation. Oops, that's not infinity, that's infinity. Okay, so then this way down is our lattice enthalpy. Clearly, all these things along here added together are going to equal these things to get added together as well. So minus 411 is going to be the same as 109 plus 494 plus a half times 242 minus 364 minus the lattice enthalpy. So if we wanted to calculate the lattice enthalpy, what we would do is we would write this out as one big long equation and then sub in the numbers. Okay, we're not going to do that for this one right now, but we will be looking at one later. So that's the standard one if we're looking at lattice enthalpy. Let's give you some new enthalpies to learn. Delta HA for enthalpy of atomization. Enthalpy change of 1 mole of gaseous atoms is formed from the element in its standard state. So for example, enthalpy change of atomization is always positive. And the example I just gave you was sodium solid going to sodium gas. Electron affinity. First electron affinity is the energy released when 1 mole of gaseous atoms require an electron to form 1 mole of gaseous 1 minus ions. And the example we just looked at there was 1 mole of gaseous chlorine atoms going to form 1 mole of gaseous chloride ions. Lovely. There will be a test on these, obviously. Here's another couple of new ones. Delta HS and delta HH. They are quite similar. Delta HS is the enthalpy change of solution, and that is the enthalpy change when 1 mole of ionic substance dissolves in water to give a solution of infinite dilution. So, for example, 1 mole of sodium chloride dissolving in water to form sodium chloride, solid. Sodium chloride AQ. And when we say infinite dilution, we mean we've got infinite amount of water between each water molecules between the two ions. Obviously, infinite dilution is a bit of a over-exaggeration. We can never really get there, but we could get close. And here we've got the enthalpy change of hydration. The enthalpy change of hydration is slightly different. That's when the enthalpy change when 1 mole of gaseous ion dissolve in sufficient water to give infinite solution. Hydration enthalpy is always negative. So this, for example, would be sodium plus gas going to form sodium plus AQ, which is totally different. This time we started with our ionic solid and we put it into some water. Here we've taken a gaseous ion and we've put that in water. Totally different. And we can do Born-Haber cycles with these. Slightly too large Born-Haber cycles for our screen. So here is a Born-Haber cycle of solution for the solution of KCl. Once again, KCl solid is at the bottom. Okay, and our enthalpy change of solution is the first one up, where we've gone to K plus AQ and Cl minus AQ. That's been an endothermic process. These won't always be endothermic. It is important to note. And we can work the same way as we did before, from gaseous ions going through their separate hydration. So we can go gaseous ions going to hydration to form K plus AQ, leaving our chloride gaseous. Hydration of Cl minus gives us ClAQ and K plus AQ. And then on the other side, if we notice, we've got at the top some infinitely separated gaseous ions, and down here we've got an ionic solid. So this is just the lattice enthalpy. This bit right here is the lattice enthalpy. So we can pop that on the other side. And then we've got a cycle that we can work stuff out with. We're going to go through a question of these at the end of this. But we're going to hold it for a second just to talk about what factors affect these values. So what factors affect lattice enthalpy? Well, Ionic charge and ionic radius. Here we've got two different lattice enthalpies. Sodium chloride, which is just between about 750, and so that would be minus 750, I believe. And we've got magnesium oxide, which is much, much higher. And the only difference between these two things is that, well, there's a couple of differences, but one of the main ones is that sodium and chloride are both single pluses, whereas magnesium and oxygen are both di-positive and di-negative. So we've got a much bigger charge, therefore we have a higher attraction between our two ionic species, and that's what lattice enthalpy is. It's a measure of ionic attraction. The other thing we need to think about is radius, and the closer two things are together, the higher their attraction is going to be. So here we've changed the size of the halogen ion, the halide. Fluoride is much, much smaller than chloride, which is much smaller than bromide, which is much, much smaller than iodide. So in sodium fluoride, the fluoride can get closer to the sodium, meaning that they have a greater attraction. Think of it this way. Here's our sodium, positive, so it's very small, and we've got a negative charge here, so the positive and negative are quite close together. Whereas if we've got a giant negative charge like iodine, it's really hard for it to get close. And the same things apply for hydration. If you have a higher ionic charge, you attract more water molecules, you attract water molecules more strongly, and if you have a smaller ion, you have a greater charge density and therefore a higher attraction. What we're going to be doing in this question is we're going to be trying to find out the well, let's read the question. We will use the Born-Haber cycle to determine the enthalpy change of hydration of magnesium ions on the two dotted lines and the species present, including the state symbols. Right, so they've given us three values, and lattice enthalpy of magnesium chloride, I can see that over here. We've got the gaseous ions and the solids, so that's going to be lattice enthalpy. We've got the enthalpy change of solution of magnesium chloride, so that's got to be this one here, because it's the only one going from magnesium chloride. So that means we're going to have Mg plus and 2Cl minus here. Okay, and they're going to be AQ, because we need to do our state symbols to get these marks. So if that's the case, then this one must be the solution of one of our types of ions, and this one must be the solution of the hydration of one of our types of ions, and this one must be the solution of the other one. We don't know which one that's going to be yet, because they've not given us they've given us magnesium, lattice enthalpy of magnesium chloride. They've given us the enthalpy change of hydration of chloride ions, but we don't know if magnesium is going to be bigger or not. Let's assume it is. So put minus 363 here. That's going to be delta H of chloride. So this one, let's say that the chloride is still a gas, and the magnesium is a Q. So this is going to be delta H of hydration of magnesium. Calculate the enthalpy change of hydration of magnesium ions. Well, we've got our Born-Haber cycle. We know this is going to be minus 2493. It's going to be minus 363 times by 2, because we've got 2 moles of it. So, and this over here is going to be minus 154. So looking at it, I can see that minus 2493 minus 154 is going to be the same as whatever delta H of magnesium is minus 363 times 2. Okay? You can just see that by the fact that these two lines are going to be the same distance apart. You could, if you want to do the same thing as you do for a Hess cycle and look for places where two things go separately, but I don't think that's always necessary. At the end of the day, you're going to be doing it's going to be a minus sign if it's going down. So let's work that out. Minus 2493 minus 154 is minus 2647. 363 times 2 is minus 726. Oops. Don't know why I did that instead of rowing it out. So we just need to rearrange now to get delta HH, which is going to be minus 2647 plus 726. And that is minus 1921. So we were right to leave this one as the bigger one. It's always going to be bigger for magnesium 2 plus because magnesium 2 plus is a dipositive ion. I believe in one of the earlier questions, one of the earlier parts of the question, you had to predict which was going to be bigger. So you would have known to leave this one as the magnesium 2 plus, but it's not too far off. So minus 1921. Does that sound reasonable? Well, yes, it probably does. It's a dipositive ion. That's about right. It looked a bit bigger than this one here, so that seems reasonable. So we can be quite happy that that is the correct answer. Okay, thanks very much.